Someone just built a ChatGPT clone that runs 530 different AI models, and it's completely free.
Wait, 530 models? How is that even possible without massive infrastructure costs? So we're exploring the model switching, this Gemini RAG integration, and how the image generation actually works.
By minute 4, you'll have it running locally with your favorite models. Let's get into it.
Welcome to the AI Daily Podcast. Today's news and a deep dive to help you stay ahead in AI.
Today we're diving into OSS ChatGPT WebUI, 530 models, MCOP, tools, Gemini RAG, image/audio gen.
Stick around to the end for this week's headlines. Let's dive right in.
So this open-source ChatGPT WebUI that's been making waves on Hacker News, 530 models, MCP support, RAG capabilities, multimodal generation. It's fascinating because it represents something much bigger than just another GitHub project. We're looking at what might be the beginning of the end for centralized AI platforms as we know them.
530 models, though. That seems like an insane number. Are we talking about different versions of the same base models or genuinely distinct architectures?
It's a mix, but here's what's interesting. They're aggregating models from OpenAI, Anthropic, Google, Meta, Mistral, and dozens of smaller providers. You've got everything from GPT-4 variants to Claude 3, Gemini Pro, Llama 2 and 3, Mixtral, and a whole ecosystem of fine-tuned models for specific tasks. The real innovation isn't just the number. It's that they've created a unified interface layer that abstracts away the complexity of dealing with different API endpoints, authentication methods, and response formats.
But that's a massive surface area to maintain. How are they handling the authentication nightmare alone? Each provider has different API key formats, rate limits, pricing models.
That's exactly the problem they're solving, and it's why this matters for platform engineers. Think about it. If you're building an AI-powered application today, you're probably locked into one provider. Maybe you're using OpenAI because it's the most mature, but then you're paying their prices, dealing with their rate limits, and you're completely dependent on their uptime. This WebUI essentially becomes a broker that lets you switch between models on the fly.
Oh, so it's like a load balancer for AI models. If OpenAI goes down, you could theoretically fail over to Claude or Gemini.
Exactly, and that's just the beginning. The MCP integration, Model Context Protocol, that's OpenAI's new standard for how AI models interact with external tools. By supporting it in an open-source implementation, they're essentially saying, we can do everything ChatGPT Plus can do, but you own the entire stack.
But wait, if I'm self-hosting this, aren't I still hitting the provider's APIs? The data still leaves my infrastructure.
For cloud models, yes, but here's where it gets really interesting. They also support local model execution through Ollama, LM Studio, and other local inference engines. So you could run Llama 3 locally for sensitive data, then seamlessly switch to GPT-4 for tasks that need more power. It's hybrid AI infrastructure.
That's a compelling privacy story, especially with the Gemini RAG integration. You could index your company's internal documents without ever sending them to Google.
And that's the revolution we're witnessing. Remember when companies had to choose between on-prem Exchange or Gmail? We're at that same inflection point with AI. The difference is, this time, the open-source community is moving faster than the enterprise vendors.
What about the multimodal capabilities? Image and audio generation in the same interface? That's traditionally been separate tools.
They're integrating DALL-E 3, Stable Diffusion, mid-journey through API, and for audio, they've got 11 Labs, OpenAI's TTS, and even some open-source voice synthesis models. Imagine building a content generation pipeline where you prompt for text, automatically generate accompanying images, and then create an audio narration, all through one interface with consistent context.
Coming up, we'll dig into exactly how they pulled this off technically, what the performance implications are, and why some organizations are already betting their entire AI strategy on solutions like this.
So let's get into the technical architecture here. How do you even build something that can talk to 530 different models without becoming a complete mess?
The key is abstraction layers. From what I can see in their architecture, they've built what's essentially a plugin system. Each model provider gets its own adapter that translates between their specific API format and a common internal representation. It's similar to how Kubernetes SSI drivers work. You have a standard interface, and each storage provider implements that interface their own way.
That makes sense, but the devil's in the details. GPT-4 returns responses in completely different format than Claude, and Gemini has its own safety filters that might block certain content. How do they normalize all that?
They've implemented what they call a response harmonization layer. Every model response gets transformed into a common schema that includes the text content, token usage, latency metrics, and any model-specific metadata. For safety filters, they actually expose those as metadata, so you can see when Gemini blocks something that GPT-4 would allow. It's transparent rather than trying to hide the differences.
Oh, that's clever. So developers can actually make decisions based on model behavior, not just capability.
Exactly. And here's where the performance story gets interesting. They're using Redis for caching model responses, not just at the request level, but they're doing semantic caching. If you ask a similar question, they can return cached results from any model that's previously answered something semantically equivalent. They claim this can reduce API costs by up to 40% in production workloads.
Semantic caching across different models, that seems risky. GPT-4 and Claude might give very different answers to the same question.
You're right to be skeptical. They handle this by namespacing the cache by model family and version. So GPT-4 responses won't be served for GPT 3.5 requests. But within a model family, they use embedding similarity with a configurable threshold. In their benchmarks, they show 92% user satisfaction with cached responses when the embedding similarity is above 0.95.
What about the MCP integration? That's OpenAI's thing. How does it work with non-OpenAI models?
This is where it gets really innovative. MCP is essentially a protocol for models to call external functions. Think of it like GraphQL for AI tools. They've built a compatibility layer that translates MCP function calls into formats that other models understand. For Claude, they convert to their tool use format. For open source models, they use the function calling conventions from the model's training. It's not perfect. Some models just don't support function calling well, but for the major providers, they achieve about 95% compatibility.
That's a lot of moving parts. What's the operational overhead look like?
The resource requirements are surprisingly reasonable. The WebUI itself runs in about 2 gigabytes of RAM. If you're using cloud models exclusively, you just need API keys. For local models, that's where it gets interesting. They've integrated with Ollama, which means you can run models like Llama 3 8B on a machine with 16 gigabytes of RAM and a decent GPU. The UI automatically detects available local models and adds them to your model selection dropdown.
So I could run sensitive workloads locally and non-sensitive stuff in the cloud, all from the same interface.
Exactly. And they've built in cost tracking too. Every request logs the token usage and estimated cost. You can set spending limits per model, per day, or per user. They even have a cost optimization mode that automatically routes requests to the cheapest capable model based on your prompt complexity.
How do they determine prompt complexity?
They use a combination of token count, presence of specific keywords that indicate complex reasoning tasks, and historical performance data. If a prompt contains code, mathematical expressions, or multi-step reasoning indicators, it gets routed to more capable models. Simple questions go to faster, cheaper models. In their tests, this reduced costs by 60% while maintaining 94% user satisfaction.
That's sophisticated. What about the RAG capabilities with Gemini?
The RAG implementation is particularly clever. They're using Gemini's embedding models to index documents, but the retrieval and generation can happen with any model. So you could embed with Gemini, retrieve relevant chunks, and then generate responses with GPT-4 or Claude. They support multiple vector databases, Pinecone, Weaviate, Chroma, and even PostgreSQL with pgvector. The index stays local, which solves the privacy concern you mentioned earlier.
Performance-wise, what's the latency overhead of all this abstraction?
They claim less than 50 milliseconds of additional latency for the routing and translation layers. The bigger latency comes from the model selection logic if you're using automatic routing. That can add 100 to 200 milliseconds while it analyzes the prompt. But for direct model selection, you're basically just paying for the API translation overhead.
Stick around. We'll give you the exact checklist for implementing this in your organization and what you need to watch out for.
So let's talk practical implementation. If you're a platform engineer considering this for your organization, there are some critical decisions to make up front.
Where do you even start? The 530 models thing is almost overwhelming.
Start small. Here's the framework I'd recommend. First, identify your use cases and classify them by sensitivity and performance requirements. For most organizations, you'll have 3 buckets: public-facing features that can use cloud APIs, internal tools that might have moderate sensitivity, and then truly confidential workloads that need to stay local.
So you're saying don't try to use all 530 models?
Exactly. Start with maybe 3 to 5 models that cover your bases. I'd suggest GPT-4 for complex reasoning, Claude 3 for large context windows, Llama 3 70B running locally for sensitive data, and maybe Mixtral for cost-effective general-purpose tasks. That gives you redundancy, privacy options, and cost optimization without overwhelming complexity.
What about the infrastructure requirements? What's the minimum viable setup?
For a proof of concept, you can run this on a single VM with 8 gigabytes of RAM if you're only using cloud APIs. For production with local models, I'd recommend a dedicated GPU node. An A100 or even an RTX 4090 can handle most open source models. The WebUI itself should run on a separate application server for security isolation. Use Redis for caching, and if you're doing RAG, budget for vector database infrastructure.
Security-wise, managing all those API keys seems like a nightmare.
It is, which is why you need a solid secrets management strategy. The WebUI supports HashiCorp Vault integration, AWS Secrets Manager, and Kubernetes Secrets. Never store API keys in environment variables or config files. Also, implement API key rotation. Most providers support multiple active keys, so you can rotate without downtime.
What about rate limiting and abuse prevention?
Critical point. The WebUI has built-in rate limiting, but you need to configure it properly. Set up per-user quotas, implement exponential backoff for failed requests, and monitor for unusual usage patterns. They provide Prometheus metrics out of the box, so you can alert on things like sudden spikes in token usage or repeated failures.
How do you handle model updates? OpenAI and others are constantly releasing new versions.
The WebUI uses a model registry concept. New models aren't automatically available. You explicitly add them to your registry. This gives you control over testing and validation before users get access. They also support model aliasing, so you can have GPT latest always point to the newest GPT model you validated, making updates transparent to users.
What are the biggest gotchas you've seen in deployments?
3 big ones. First, context window mismatches. Users try to send 100K tokens to a model that only supports 8K, and things break. The WebUI has safeguards, but you need to configure them. Second, cost explosions. Without proper monitoring, a single user can rack up thousands in API costs with long-running conversations. Third, compliance challenges. If you're in a regulated industry, you need to ensure your audit logging captures not just the prompts and responses, but which model was used and whether data left your infrastructure.
Speaking of compliance, how does this work with data residency requirements?
That's where the hybrid approach shines. You can configure routing rules based on data classification. PII or regulated data gets routed only to local models. The WebUI supports request tagging, so your applications can mark requests with data sensitivity levels. You can even geofence certain models, only use EU-based deployments for EU data, for example.
That's powerful. What about the future? Where's this heading?
I think we're seeing the emergence of AI infrastructure as a first-class platform engineering concern. Just like we went from managing individual servers to Kubernetes orchestration, we're moving from individual model APIs to AI orchestration platforms. These open-source WebUIs are the early versions of what will become standard infrastructure.
Any predictions on how the vendors will respond?
They're already adapting. OpenAI released MCP partly because they see the writing on the wall. Lock-in at the API level is not sustainable. I expect we'll see more standardization, better tooling for hybrid deployments, and possibly even vendor-provided versions of these multi-model interfaces. The smart vendors will embrace it and compete on model quality rather than API lock-in.
So the actionable takeaway for our listeners?
Start experimenting now, but start small. Set up a proof of concept with just a few models. Focus on solving one specific use case. Maybe it's giving developers choice in their AI coding assistant, or creating a fallback for when your primary AI provider has issues. Learn the operational patterns before you bet the farm on it. And most importantly, treat this as infrastructure, not just another app. That means monitoring, security, capacity planning, all the platform engineering disciplines we've learned over the years apply here too.
This really does feel like a paradigm shift in how we think about AI infrastructure.
It is, and here's the thing. The organizations that figure this out early will have a massive competitive advantage. They'll have lower costs, better reliability, and more flexibility in their AI capabilities. The age of single-vendor AI lock-in is ending. The question isn't whether to adopt multi-model strategies, it's how quickly you can do it safely. Before we wrap up, let's catch up on this week's infrastructure news.
There's a fascinating new development in the AI world. ChatGPT is now pulling information from Elon Musk's Grokipedia, according to TechCrunch. This conservative-leaning, AI-generated encyclopedia is becoming a source for ChatGPT's responses, though the system apparently avoids directly citing it on widely debated topics.
That's interesting timing, especially given the ongoing debates about AI bias. How does ChatGPT decide when to use Grokipedia versus other sources?
The article suggests it's selective. ChatGPT seems to pull from it for certain topics while avoiding attribution on controversial subjects. It raises questions about transparency in AI sourcing.
Speaking of AI development, there's major news from the research community. A new paper on Archive introduces AgentDrive, an open-source benchmark dataset with 300,000 LLM-generated driving scenarios.
This is huge for autonomous vehicle development. The dataset includes AgentDrive MCQ for evaluating how AI systems reason through complex driving situations. It's completely open source, which could accelerate progress in the field.
And on the hardware front, Microsoft just announced the Maya 200 chip specifically designed for AI inference. TechCrunch reports this is part of their strategy to reduce reliance on NVIDIA.
The chip promises improved speed and efficiency for running AI models at scale. It's fascinating how tech giants are all developing their own silicon now. Microsoft joining Google and Amazon in the custom chip race.
Meanwhile, Apple's making moves too. They're reportedly unveiling a Gemini-powered Siri assistant next month.
According to TechCrunch, this February update will finally fulfill Apple's AI promises from last year. The new Siri will supposedly access users' apps and data more effectively using Google's Gemini models.
It's an interesting partnership, Apple leveraging Google's AI tech rather than going it alone. Shows how competitive the AI assistant space has become.
That wraps up this week's news. That's our show for today.
If you found this valuable, please subscribe and share with a friend who'd appreciate it.
Drop us a comment with your thoughts on today's topic.
Links to everything we discussed are in the show notes.
Until next time.